Hey, Math 137, what's up? In this video, we're going to be taking a look at the fundamental trig identities and showing you derivations for where they come from. We are going to be discussing these in class, maybe not as completely as I would like, but I do want to take time to show you where the identities come from. These are, I guess, our proofs are going to be related to our right triangle definitions for the trig functions, where we have a right triangle with an acute angle theta, and we labeled the side opposite to theta, the side adjacent to theta, and the hypotenuse, so the lengths of those sides. And we had our right triangle trig definitions as ratios of those side lengths. And then we also discussed in class the reciprocal identities. We can see that sine and cosecant are flipped fractions of one another, so that means that cosecant is the reciprocal of sine. Sine is the reciprocal of cosecant. Similarly, secant of theta and cosine of theta are reciprocals. Cotangent of theta and tangent of theta are reciprocals. And again, we can see that they're reciprocals just by looking at the definitions. They're just flipped fractions. The next batch of fundamental identities are often referred to as the tangent-cotangent identities. And the tangent identity says that tangent of theta is equal to sine of theta divided by cosine of theta. So let's look at that real quick and see why it's true. If I take sine of theta would be opposite over hypotenuse, divided by cosine of theta would be adjacent over hypotenuse. So again, this is sine of theta over cosine of theta. Remember, division is the same as multiplication by the reciprocal. So if I want to take opposite over hypotenuse and divide by a over h, that's the same as multiplying by h over a. Our h's cancel. We get opposite over adjacent, which is exactly tangent of theta. So that is why tangent of theta is equal to sine of theta over cosine of theta. Similarly, if I take cosine of theta and divide by sine of theta, well, cosine is adjacent over hypotenuse. Sine is opposite over hypotenuse. And again, when we simplify this, division by O over H is the same as multiplication by H over O. H's cancel. We're left with A over O, adjacent over opposite, which is exactly our cotangent of theta. So the two identities that fall under the banner of tangent-cotangent identities, tangent of theta is sine of theta over cosine of theta, and cotangent of theta is cosine over sine. The other batch of fundamental identities are called the Pythagorean identities. So there's three batches of fundamental identities. There's the reciprocal identities, the tangent-cotangent identities, and the Pythagorean identities. The first Pythagorean identity says that sine squared of theta plus cosine squared of theta is equal to 1. Now, that notation is a little bit wonky, so let's talk about it for a second. We use some slightly unfortunate notation with the trig functions. When I want to take the number sine of theta and square that number, we often denote that by sine squared of theta. There's no exponent rules going on here. We're not distributing the two. It's not any algebra that's going on here. This is purely notation. All right. It's like if if we want to say that, okay, the word the two words do not, we can kind of form them into one word called don't. That there's nothing going on there. That's just how we write the word. Sometimes do not, they don't. Okay, this is just how we, the sine squared theta. That's just how we write sine of theta quantity squared. All right, so don't let that confuse you any more than it absolutely has to. There's no, I guess, there's no understanding here. You don't understand why this works. This is just how we write things. Okay, so back to our Pythagorean identity. Let's see why the first Pythagorean identity is true. If I take sine squared of theta, well, that's the same as sine of theta squared. Again, that's how we write it. Plus cosine of theta squared. Sine of theta, from our right triangle definition, is opposite over hypotenuse. Cosine of theta, from our definition, is adjacent over hypotenuse. If we use now here we are using properties of exponents to say that this is O squared over H squared plus A squared over H squared, and we're using properties of addition of fractions to say that this is O squared plus A squared over H squared. Now, if you remember, we're talking about O and A and H are side lengths of a right triangle. And we have a Pythagorean theorem that says that O squared plus A squared is equal to H squared. So, back over here, O squared plus A squared, that is equal to H squared on top, and H squared divided by H squared is equal to 1. So, that is why sine squared of theta plus cosine squared theta is equal to 1. And the fact that we use the Pythagorean theorem here in this next to last step, that gives you an indication of why we call this one of the Pythagorean identities. Right, there's two other identities, one of which, if we take everything in this first Pythagorean identity and divide by cosine of theta, or sorry, cosine squared theta. We can use some properties of exponents. Sine squared of theta over cosine squared of theta is the same as, I guess just from notation, sine of theta squared over cosine of theta squared. The second fraction is just equal to 1. Cosine squared divided by cosine squared is 1. Or cosine squared theta divided by cosine squared theta is 1. And I'm not going to do anything with this, I'm going to go call this 1 over cosine of theta squared. And then now if we use properties of exponents, we can say that this is sine of theta over cosine of theta squared. And this is 1 over cosine of theta squared. So the property of exponents that I'm talking about here is the one that says that a to the n over b to the n is equal to a over b to the n. Okay, now we have, let's see, from our tangent, cotangent identities, sine of theta over cosine of theta is equal to tangent. So this is tangent of theta squared. And from our reciprocal identities, 1 over cosine of theta, back here, there it is, 1 over cosine of theta is the same as secant of theta. So this is secant of theta squared. And then finally, again, just because of notation, tangent of theta squared, another way of writing that is tangent squared theta. And secant of theta squared, another way of writing that is secant squared theta. So that's our next, this right here is our next Pythagorean identity. Tangent squared theta plus 1 is equal to secant squared theta. So we'll write that one down. And then the third Pythagorean identity is 1 plus cotangent squared theta is equal to cosecant squared theta. So those are the three Pythagorean identities. We actually used the Pythagorean theorem to prove the first one, and then we used some other strategies to prove the second one. The third one, you could use a similar strategy. You could take the first, you take sine squared plus cosine squared equals 1 and divide everything by, instead of dividing everything by cosine, you can divide by sine and see where that leads you. You could also, the Pythagorean theorem could also be used to prove or derive either of these two as well. So those are our fundamental identities. Again, the three batches, the reciprocal identities, the tangent-cotangent identities, and the Pythagorean identities. Those are the three batches of fundamental identities. We're going to be working with these identities for almost the entire semester, and you're going to know these like the back of your hand. But again, I wanted to take the time here in this video to show you where these identities come from, just to convince you that we're not making it up just to make your life hard. These identities do establish a relationship between the trig functions, and these relationships end up being very, very useful. All right, that'll do for this video. Thanks for watching. If you have any questions about it, please let me know.